I tend to make these introductions fairly short. Bill, come on up. Bill Peter is the director of DOE's first manufacturing demonstration facility here at Oak Ridge National Labs, and can't wait to see his talk. It should be really exciting. So, thank you very much, Bill.
Yeah, thank you very much. So I'm this is a little different talk than I normally give. I've weaved in a little bit of what are we doing today at the MDF. I'll get a little bit into some of the things that Alan had talked about. I think he set it up very nicely to show what is the state of the art, where are we going in manufacturing. But I've tried hard to apply this to the materials and concepts as we would look at trying to fabricate things in space and use those materials that we would find there. So I've weaved in a little bit of what technologies would we be thinking about, and how would we go through and look at depositing things like moon dust and meteorites. And so I'll try to capture that as we go through. So let me first just take a step back and explain what is the manufacturing demonstration facility and what's my job and what does this look like. So the manufacturing demonstration facility was really born in 2011, at the very end of 2011, and Oak Ridge National Laboratory was doing a lot of good work in advanced manufacturing for DOE projects, but really did not have a vehicle or a way that companies could come in and work with us. And the whole idea was really trying to reinvigorate U.S. manufacturing, bring together a group of people from all different directorates and divisions, and really try to co-locate them and apply them to specific areas of need. And what you get is about 200 people with a huge range of diversities, everything from computer science, material science, mechanical engineer, coming together to look at how do we raise the state of the art in advanced manufacturing. We've got different ways of how we work within the MDF. We have our core research and development. We've put a strategic plan together that really lays out why should Oak Ridge be engaged in this area and where are those holes that we're trying to fill in. I'm going to touch on that in the next slide here. But one of the true benefits of the way this was set up was the idea that we can also engage education in universities and get students involved. We get about 100 students every summer that are engaged. Have helped put governor's chairs at the University of Tennessee, where we have about 50 students under those governor's chairs that come over and work with us on a daily basis. And then also created the ability to have what we call industry collaborations, where we're sponsored by the Advanced Manufacturing Office under EERE of Department of Energy. The Advanced Manufacturing Office has been nice enough to put funds down each year so that when companies see what we're doing, they can actually write a proposal and cost share a project with us, do a collaborative effort on how do these technologies apply to their areas of interest. That's been highly effective. We've had over 140 of those projects. The last thing I'll mention is, and you'll see some of this as I go through some of the slides, is what we call demonstrations or moonshots. We've pushed very hard in certain areas in very short time periods to try to change the state of the art. Quite often these may not be done, I may be printing or additively manufacturing something that I would not do as the normal way of production, but it pushes where are we within the manufacturing technologies, where are the big challenges, how do we get the right people together and integrate the supply chain. So it's really important activities. We've done things like printing different parts of excavators, printing a submarine, printing cars, just for examples. So here are the 4 areas that we're really concentrated on. Where I mentioned the challenges or the areas that we continue to look at, and you're going to see this through the presentation that I give. The first is materials. A lot of the materials that were designed for additive processes really had different origins. They were either made for casting or for forging, not necessarily the time at temperature as we get into additive processes. And so we spent a lot of time on redesigning or rethinking these materials. I think this aspect is going to be very important, and some of the things that we've learned from that as I start talking about some of the materials that we would have to start looking at where I don't have a choice. If I'm looking at a meteorite and trying to understand the materials, what would I be capturing from that? As well as moon dust. So I'll talk a little further about how are some of the activities that we're doing in materials development, how would they impact the challenges we would have to overcome as we get into those areas. The next is a qualification and certification. One of the big issues with additive manufacturing is it is a temporal and spatial process where you can modify the process parameters as you're building parts. Now this is great in one sense because it means we can, through microstructure and through the way that we deposit, really be able to dictate how will that part perform. But the issue is that we have based our qualification and certification on a historic statistic base, and that becomes very difficult when you tell me that I can change the process as you go. And so we have to rethink the way that we go through and develop this. Alan mentioned the idea of born qualified. That is a concept that we're continuing to develop. I'll talk a little bit more about that as I go through this presentation. We also spend a lot of time in modeling and characterization. I'll show how that applies a little bit to the different things. And I think one of the bigger areas that I wanted to impart today is our developments in AM systems. So we continuously are trying to change the concept of what are we able to do in additive systems. One of the things you'll hear me talk about is not just looking at it from an additive perspective, but how do I come up with a hybrid solution that can deposit, machine, and engage with other advanced manufacturing technologies in order to give a finished product that I can utilize. And of course, this would be very important as we try to automate a process of how would you build things in space. So let me go through just a little bit on the materials just to give you some idea of what type of materials have we been working on. The first two are areas that I'll step down into further. One is high temperature nickel alloys and refractories. Additive is very good for being able to create complex geometries where I can take materials that are generally very hard to form or fabricate. And one of the things that we find is as we get into some of these high temperature nickel alloys that I'd really like to create is the fact that they have a tendency to crack. Through additive, we can actually look at how do we modify the thermal history of that part so that we don't get cracking. We've also shown the idea of being able to specifically control microstructure as we deposit parts based on welding theory. So changing the liquid-solid interface velocity and the thermal gradients, you can manipulate and go from long columnar grain structures to equiax grain structures, and therefore, in the same part, be able to locally dictate how will that part perform. The next area is looking at advanced steels, and in the advanced steels, we are looking at the idea of how do we change the chemistries of the steels to help create the geometries we want. So one of the things as you start going through, additive manufacturing is essentially looking at how do I weld parts. It's a way of thinking through and saying I'm going to weld the entire part to construct to finish that component out. And one of the big issues as we go through and do that is the residual strain and stresses that are a result of the thermal gradients as you start producing that part. We've started looking at the tailoring specific steels where can we change the transition temperature and go from tensile residual stresses to compressive residual stresses to effectively be able to change how that part as we're forming it, how easy it is to create that geometry. And so it's going through and thinking through those type of processes that are really interesting. We also have started looking at gradation and hybrid materials and composites. So this idea of putting materials where I want them site-specific in order to enhance performance but lower cost. We've done a lot of this work in, for example, creating a low-carbon steel with a stainless steel or a tool steel on the outside for those areas where I would have wear or degradation. But you can also start thinking about Ashby type hybrid material systems and how you can effectively look at multiple materials and how you put those networks together and how that can provide really interesting property sets. I want to move a little bit from the work that we've done and talk more about some of the activities that have been very similar to things we've been doing but have been specific to moon dust and meteorites. So if I look on the left side for you, this is some of the work with NC State where Mahal had a dissertation on electron beam melting, so using a RCAM system. This is a process where you lay out a thin layer of powder, an electron beam goes over that powder bed and locally melts the material. He ended up using lunar regolith simulant, JSC1, to go through and evaluate this material. Now, there's inherent difficulties in trying to go through and fabricate these. You're essentially dealing with a big composite of ceramic or oxide type materials. And just to give an idea, silicon dioxide makes up 50% of the material that they were evaluating. One of the issues, so electron beam has high interest because of the fact I can operate in vacuum. So there's inherent benefits as I go into looking at how I do this in space. The issue, though, with it is as I go through and use the electron beam to try to melt things, you're also ionizing. So if you start using a particle-based approach, you ionize that bed if it can't be highly conductive. And so some of the issues that they ran into were charging of powder particles. One of the ways they got around that was looking if they could ball mill aluminum around the regolith simulant. And by doing so, from 25 to 50%, they showed they could build up structures using that way. They obviously also wanted to go, 50% aluminum would be a lot of aluminum we would have to take up into space. So they also wanted to see, could you go through and deposit it in a pure sense? And they found with low voltages to prevent from charging, you could actually go through and deposit. However, once you started building a large enough structure, it would cut off because you would not have conduction for those electrons through the part you were building. So it was layer limited. Another project was looking at the idea of electron beam weldability. So using a electron beam that you would then take material, almost like you would think welding, and free form start building parts from it. They were doing this with iron meteorite. It was a group led by Elmer out of Lawrence Livermore National Laboratory. The material they were evaluating was Canyon Diablo meteorite. You'll notice it when we start talking about most meteorites, you're talking about a high iron and nickel composition. One of the challenges as we look at this, though, is every time I go through and think about a meteorite, you may be dealing with a different material composition as we start to think about how we go through and deposit it and having to work out the process parameters as you think about those. So they were able to show that I can go through and weld these materials. One of the issues, though, as you start looking at is there are small amounts of sulfur and phosphorus. And these are typically thought of as really bad materials to have in our steels as we try to weld them. And so one of the issues that you find is I get cracking. Now, since this work in 2014, there's been some activities at Vanderbilt in looking at friction stir welding. This is a solid state technique where you basically plunge a nipple into the material and rotate it. You can extrude material this way and then go through and basically bond it in a solid state fashion. And so there's been some work in trying to come up with alternatives. We have also alternatives that we've started looking at, and it goes along the lines of how we go through and do these high temperature materials. So in the electron beam system that I just mentioned for some of the lunar regolith, we've gone through and actually created new scan strategies that change the thermal history within the build. So typically these systems go in a serpentine type scenario where line by line you build up your part. We've basically said, look, I can go through and make little local weld pools, do these in spots, and change the way that we lay these out in time. And you can basically, through modeling, effectively show how I go through and bring that full bed up to temperature. And by doing that, regulate that temperature and make sure I don't get cracking. So we've done two things as we've gone through and have done that. The microstructure control, this has also been an excellent way for us to go through and look at the idea of creating crack-free parts. And in fact, over on the bottom right is essentially some work we've been doing with nickel, high temperature nickel. So MARM 247, 738, we've been able to create crack-free parts through use of this type of technique. And have even started looking at refractory metals, so going even higher in temperature, more difficult materials to go through and develop. So this may be a way to solve some of the issues and the impurities that we see within these materials. Of course, that will not fix the embrittlement and some of the other things we have to look at with carbon and having the impurities still there. I also wanted to bring up, before I start showing some of the systems that we've been working on, some of the work that NASA's been doing. There's been different efforts in looking at large-scale directed energy deposition to create structures. NASA has funded activities in what they call electron beam freeform fabrication and even have patents in this area. One of the nice parts, once again, it is an electron beam, so it works great as we're looking at the idea of space. They've used wire to go through and as their feedstock for deposition. The idea for wire, and this is another difficulty that would have to be solved, is in a lot of these processes we use powder or particulate. Of course, in zero gravity effects, that could be a very difficult material to work with. That's partially why NASA has said, let's focus on wire and see how we can go through and produce parts using electron beam and wire. They have done low gravity experiments in parabolic flights. I think the last one was in 2007. They've even made graded structures. You can see this one where it was an Inconel nozzle with a copper insert that was built inside of the structure. I think this is a really nice type of process to look at. Of course, as we look through this, you would have to figure out, how do I produce the wire, or a way to take your aggregate and be able to put it into a form that you could feed on a regular basis. At Oak Ridge, we are continuing to push the concept of large scale, and we're doing it with a whole range of different technologies. Everything from MIG welders to TIG welders to lasers, and really going through and fabricating large parts. We pick different systems based on the materials we're looking at. For example, if I want to do steel, I'm usually doing it with a MIG welder because of the low-cost nature of MIG welding. And the fact that I'm not so worried about some of the impurities or interstitials that I would get with something like titanium or some of these other materials. These systems are getting larger and larger. As we start going through, we're even thinking about hybrid approaches. So this timeline shows several of the different systems, starting with the TIG welding that we initiated with, going to working with Lincoln Electric and Wolf Robotics on a MIG welder that's now commercially available. We have a significant project with GKN where we're laser fusing titanium alloys to make near net shape aerospace componentry for them. In March of 2017, we printed the stick on the excavator that you see up here. That was about a 5-day build. Some of the more recent systems are allowing for the idea that I can interchange the head. So you can think of, I print with a wire for my bulk, and then I can grade the property sets and go to a powder as I get to a finer resolution on the outside and want to grade the structure. This leads me sort of to what I'm looking at for the future system. Where are we headed? This is a cell that we'll end up getting at Oak Ridge in the next month. And we've affectionately called it Medusa. That's the top right one you see. It will have 3 MIG welders, all on robotic arms, on a turntable, building up really large structures. Part of the difficulties for us is getting those robots to work together, really trying to figure out how do we go through and seamlessly have it so they're integrated, be able to deposit in a controlled fashion, controlling the geometry that they're printing, but also be able to go through and interchange heads where I can go to machining and other coating type techniques and pick and place techniques directly in the unit cell. So one of the things that we go through is right now as we look at major manufacturing, you have a distributed manufacturing scenario of I build it or I cast it, I forge it, I machine it type scenarios. We're really trying to say, can I take a unit cell and do everything inside that cell? One of the nice parts about this and that I like is the idea that robotic arms and MIG welders are not very expensive. So this is actually a very affordable way to looking at how we could go through and start producing out of parts. The system of the future will have real-time correction, and I'm going to show that in just one second, and also be able to provide more than one material. So can I go through and lay down materials where I want them? I will say as we looked at this system, we will be doing INVAR materials, which is an iron nickel material. And so though it is not asteroid material, it is getting closer to those chemistries that would be of interest. So one of the issues that we're going to see is uniformity of the materials as you start to go through and try to mine something like an asteroid and say how regulated is the chemistry of it. We spend a lot of time as we fabricate components and going through and making sure that that chemistry, the microstructure is uniform as you're going through and producing parts. This is going to be a very big challenge because it's going to mean that as I deposit these, I won't know what the performance of it is. And so really having to come up with new methodologies. One of the ways that we've developed or looked at this is creating a digital twin or a born qualified scenario as we're building these parts. So we've started working with the Air Force on a system called Dream 3D. This is basically, think of it as a map, a file cabinet map, where I can go through and store voxel by voxel data of what I'm planning to build, what I've been modeling, what I see while I'm printing the part. So a lot of our printers have near IR or IR cameras directly on the system, high-speed cameras. You can put X-ray detectors. And so as you're building this part, evaluating real time and storing that information. What's nice about this is as you engage this and build this up into a structure, I can create data visualization tools like what you see on the bottom left so that I can start understanding how does this process parameter change the results that I see as I'm printing it. So a better understanding of the overall process itself. But then you can also, as your confidence builds up, you can create controls so that, and machine learning, so that if you start to go out of your confidence bands, can I real time make changes to the system so that it gets me back on track and gives me reproducible results. This starts going to this idea of an artificial intelligence or machine learning that basically goes through and gives me results that I can start to concentrate and really understand what I'm going to get. And this is just one example where we've basically taken microstructures of materials, analyzed them real time, and then be able to go through and tell you, predict, how is material perform. What has resulted from all these things that I've talked to you about? Well, we've gone into much larger objects. We're looking at a lot of energy systems and how we can go through from hydro and making small modular hydro systems to wind turbine blade molds, molds for producing buildings, looking at materials to go into gas-fired furnaces, as well as looking at repairs and transportation. So for me, it's not that large a step as we start looking at thinking about how would you do this in space, and what size scale would I need to go through and demonstrate for it to be useful for us going forward. This is my last slide, and I basically just want to say as we go into this, if there's specific interest, I explained that we have quite a few ways that we engage with industry as well as academia, and we do have a lot of visitation to our facility. Please let me know. You can get in touch with me, and I'll be glad to set something up so you can see what we're doing. I think getting around the equipment, I can give you a slideshow all day. It will not give you a full sense of what's really going on without actually being around the equipment and seeing how this is coming together to change the way we manufacture goods. That's the last one. Thank you.